super late to the party. Hey, Jaden, are you recording yet? Okay.
I should be.
I think D might be. Okay, awesome. For those who are not here today or here earlier, and also for the video that I forgot to record for the first section, today's workshop is going to be on PID. PID stands for proportional integral derivative, and then with a combination of these three constants, you're able to correct your margin of error, right? P is for kind of how hard you're trying to get to a certain position. I is your margin of error due to time. You're trying to adjust for that. So this could be like gravity or something. And then derivative is going to be trying to dampen or slow down your mechanism when it is kind of oscillating around its set point in order to not overshoot your goal. And the order you should probably tune your PID in is going to be P first, P for proportional position, and you're gonna increase until it oscillates around a set point. So if you had a graph like that, it's going to oscillate like this around its set point. And that's how you know you found your P, right? Your derivative is going to, and after you tuned your P to be oscillating, you're going to increase your D till your set point line and your derivative line is basically like lined up together. I wouldn't tune integral, just keep it at 0, because that could cause a lot more backlash and like unpredictable mechanism movement, and usually is unnecessary unless you really, really want to. Sure, but don't touch integral. That's rule of thumb for now. Unless another expert says so, I wouldn't touch integral. Feed forward is going to be how you predict how much power you need in order to get to your position. So where PID corrects your margin of error, feed forward predicts how much power you need before error happens. And you're doing this by adjusting your KS, KV, KA, and KG. KS is going to be anything related, adjusting for static friction. KV is compensation for velocity. KA is for acceleration. And then KG is going to be for gravity. When you're tuning something like a arm or mechanism, you want to kind of start with either KS or KG. KG if it's struggling to hold its place on, it's holding, you're trying to hold a arm at a 90-degree angle and it's struggling to hold its position, you should probably tune your KG till it is able to hold. And then if your mechanism is even struggling to lift itself, try increasing KS by 0.1 or 0.2 in order for it to start moving, lift itself. However, be very careful when you tune these values because, once again, it's trying to predict these values or your gravity, your static friction to output a goal of amount of voltage you need to reach its goal. And when you if you tell it lies and say, hey, I need 100 kgs in order to overcome gravity, whatever, it's gonna believe that and it's gonna break your mechanism. So increment slowly. You can also trust your life with SysID. Usually pretty accurate. From what I've heard, nothing has gone totally super wrong with using SysID to tune your mechanisms. I think that was what our first workshop was on, about SysID, if I remember correctly. But yeah, with a combination of PID and your feed forward, tuning these will allow you to have a smoother mechanism, whereas if you tune it very poorly, you could have the risk of your mechanisms breaking. So be very careful when you tune these mechanisms. And then there are some things you should know about for trying to control your mechanisms, and that is going to be motion profiles. Motion profiles help you adjust or it tells your mechanisms how to move, right? Whereas PID reacts and feed forward predicts Motion profiles are controlling the entire process. Trapezoid profiles move like a trapezoid, you see here on the graph, and it limits the acceleration velocity of feedback and feed forward. This is a graph of what it is. So you see how it's split into three parts: acceleration, constant velocity, and then deceleration. And these constraints on a trapezoid profile and the max velocity are the max velocity and max acceleration. So that's how much your mechanism, that's the limit for trying how fast to accelerate, how fast you should hold that speed, is because you set your max acceleration, max velocity somewhere in your code. Here, reasons why you should use a trapezoid profile is because you have full control of your mechanism's entire motion. You can control its moment of its inertia for smooth transitions between set points, and improves repeatability despite changes in motor load. To create a trapezoid profile, it looks something like this. You create your smart motor controller config, and then your closed loop controller. You have your PID values right here, right? And then you have your RPM per second of right here. And you're gonna notice that, hey, this kind of looks a lot like my code or whatever your code looks like. And it's because this is your code. Trapezoid profile is usually kind of the default one that most FRC teams use, especially in YAMS. That's kind of the default one that's already made for you. If you haven't declared that you're using something different, you're going to be using trapezoid profile. And so to recap, that is the one where you're controlling, it's split into three parts with its acceleration, constant velocity, and deceleration, very linear, right? Exponential profile, on the hand, is a little bit more advanced, but it allows you to have smoother control over rougher mechanisms that experience some kind of friction that the feed forward and feedback alone can't easily overcome. So the constants are going to be kV and Ka. The kV represents the voltage that is required to maintain a given velocity, and Ka represents the amount of voltage required to apply a given acceleration. Once again, very familiar to the concepts we talked about before when we were talking about our feed forward our feed forward loop. Here's a graph of it kind of, let's see, PID position, reference slope. I'm guessing this is trying to showcase that. Can't really comprehend it though. Maybe a little slow. Okay. kV represents the voltage required to maintain a given velocity, your voltage and then your angular velocity. And then it does this by dividing the supply voltage by its kV, which results in the maximum velocity of the profile. And then when the supply voltage is fixed, the higher profile kV results in a lower profile velocity. It is safer to start with a higher kV when it is ideal. So it looks something like this. It's once again very similar to how you created your trapezoidal profile controller, and it looks something like this. You got your PID values. You set a new object. You create a new object called PID profile. Exponential profile PID controller. And then you have your PID values. You set your constraints, which is once again your kV, your Ka, and then your volts per second. Let's see. For every mechanism, it's going to look a little different. So you have your your arm, and its parameters are going to be your max volts, your DC motor, that motor that you're using, your weight, arm length, and gearing. Yes, the slides will be shared later. I also have a video where I went through over the more mechanical and kind of the motor configs of this. So I have one video talking about the first section, which is about the mechanisms, and then another video about all the configs. And so this one is going to be all about how to like tune all this stuff from your motion profiles, and then how to tune PID, which is a video I have been putting off for a very long time, and which is now why I'm doing it right now. Responsibilities. Okay, yeah, so that's what an arm looks like. Most importantly, you're kind of putting in the arm length. That's kind of the most defining thing, and also the gear ratio. Yay for responsibility, I agree. And then you also can do it for your elevators. Make your elevators really smooth. You got your max volts as its parameter, your DC motor, your carriage weight, so how heavy your elevator is lifting, not like how heavy your elevator is in total or how your robot is in total. It's going to be that weight. Your elevator's height, so that's going to be its max height, not like if you have an elevator and you stuck an antennae on it. No, it's going to be how high it's trying to lift. And then you're going to have your gear ratios. And, you can do this by new mechanism gearing, or the bajillion other different ways you can set your gear ratios, because we love redundancy. Same thing with flywheels. You have your volts, motor. You're going to be having your flywheel weight and your wheel radius, as well as your gearing. And then finally, you have, simple mechanisms. You got your max volts, angular velocity, and angular acceleration as parameter. And I forgot what simple mechanisms are used for. I think it's just for use cases where, like, it's not a flywheel, it's not an elevator, it's not an arm, it's just simple. On to tuning. Actually, I remember the slideshow I had where I feel like it showcased the difference between, Exponential and Trapezoid very well. Let's see if I can find it. It was the one that we used to present, Jaden, right here. Level up your program. Let's see. Boop, boop, boop. Do. So this slide is already sent out here. Talks a lot about YASS. This is what we use to program, kind of, present about. This is crazy though. If you haven't used YAMS yet, you should, because this is our original elevator code for the last season. This is YAMS elevator. In our off-season robot, same game, whatever, but the length on how to program basically the exact same functions is significant. It's cut in half. And when I made this graph, I was actually mind blown by that. Also, all of this is actual code, so it's not faked. Trust me, I wouldn't never. Okay, features. Nope. Appeals. Nope, this one. Okay. Ooh, the GIFs don't exist in Canva. How fun. Okay, but this showcase as well. If you had the GIFs, it would basically be really smooth compared to this one. This one's way smoother. PID requires the same responses at all input levels. It is consistent. It uses consistent outputs at all speeds, and is best for slow, accurate movements. Whereas your exponential profile, it has small inputs and gentle control. For gentle control, where you also have large inputs for more faster and powerful response, and this enhances its smooth acceleration and deceleration. So it's once again very smooth. It's able to kind of adjust between different set points very easily compared to a regular PID thing. And now let's on to tuning. Okay. Prerequisite for CTRE users. if you do not want to split screen advantage scope while tuning tuning with Phoenix while tuning, you can publish the Phoenix 6 signal that you'll need to add by the following. So if you're using CTRU motors, whatnot, I'm pretty sure you can get the signal lights to tell you how much your graph or whatever advantage scope tells you, which is interesting. My team uses a lot of revs, so I'm no expert, but to have this, you just after you create your motors and your mechanism, you're going to create a object for the signal lights, and then in the public elevator, you're going to set your base signal status and periodic. You're gonna have all this logged and then outputted for you. And now let's get into the order of how you should tune your PID. So first, you're going to limit your max velocity and max acceleration during tuning to prevent damage, and then set literally everything to 0. The only thing I probably wouldn't set to 0 is KP. I would set that to maybe 1 or 2 because those numbers is probably not going to kill anyone. PID 1 or PID 2. Anything like starting with 5 scares me sometimes. Let's see. I don't know if you guys have played this with YAMGen yet. Let's see. But YAMGen is kind of a great way to get even your mechanical team to practice your PID. Alright. This is a simple elevator. If I go over here in my motor configurations, control configurations, I can tune my PID. If it's starting at 1 right now, and that's how it moves. If I set it to 0, I'm pretty sure it's like struggles real badly. Yeah. So this is its set point, and this is its actual current state, and you want these to line up. And to do that, I'm going to tune my PID. I'm only going to PID only, because I'm kind of trying to demonstrate, what PID does. So I'm going to just do some crazy value first, like 5, because it's sim. I'm not scared of mechanisms breaking. And you see, yeah, so it's getting closer to its set point, and it's not exactly oscillating towards it either. Maybe this is accurate based on WebSim, although every time I change, notice how it is kind of oscillating towards that. And honestly, I think I do need to adjust my kg because it is not lifting itself. So let's run it. Ooh, okay. I'm gonna set this back to 1, and then if I run this, you see the effects of kg now, right? If I increase it, it kind of just sets it to some kind of height. So once again, increment very slowly. This is your warning. You've heard it here. So now, okay. I think I'm able to tune this with a little bit more kg. Yeah, there we go. That's pretty close. So, and then I can make it a lot more smooth by increasing my KD a little bit. That way it's not so jittery every time I'm moving my arm. Of course, I only did that for 5 minutes. Sometimes yams or tuning can take hours, 6 hours even, if you're trying to get it really smooth. So make sure you save a lot of time to tune your robot. Bit of random question, but why is there an entire import statement for a angle class just in the constructor? Let's see. You mean, where did you see that? The constructor. On the first example. I said a lot of first examples, man. Were you talking about it in YAMGen? Because generated code. Oh, they do have access to these slides? You're just on it. Here? Where? Oh, here. I think whoever made this probably just straight up kind of, yeah, I don't know. They just imported in there. Maybe they were using a class that had, or they were using a project that has this straight up built in. Maybe they cloned it from WPI lib. But yeah, I guess that's one way you can import that. I guess it leaves the guesswork from actually assuming that you know how to import this and just straight up put the import there. Yep. Okay, I think I digressed a lot. So first step, set your limits. Yeah. Second step is going to be finding the kg that holds your mechanism in the air. Talked about that already. I'm not gonna. Yeah, sure. I will digress because this doc is actually really cool. This slide you see here, they kind of tell you the exact same thing on how to tune kg, kV. And yeah, y'all should check it out. It's for the simple arm, which let's see. Okay, I need to stop digressing though. Find the kV that allows the velocity portions of the position and the reference graph to have the exact same slope. Let's see how to define that in simple terms. Okay, so when you have your graph, let's see, where's the graph? Position, velocity, kind of want to have that in a sense in a pretty close together line. Allows your velocity portions and your of the position and the reference graphs to have the same slope. So yeah, when you're tuning your mechanisms in an Vantage scope or whatever site you're using, you're gonna have your position and you're gonna have all your like kV and your set point values. You would make sure to have this. So tune kV. Let's see. How to say? Increase kg, increase the velocity feed forward kV until the arm tracks the set point during a smooth slow motion. If the arm overshoots, reduce the gain. Yeah, so it's just like trying to track its position. You can do a lot with just kg, kV. And then after that, you can tune your Ka that allows the acceleration portions of your reference graph to have the same slope. You mostly care about the acceleration part here, not the deceleration yet. So this is just making sure your arm is kind of up to how you like it. And then you're going to increase your Kp till the mechanism overshoots and then backs off until the undershoot stops. Overshoot stops. Let's see. Basically, increase your P till it oscillates around its point, right? And then, because it's going to be overshooting a lot, and then when you're increasing your KP, it's going to try harder and harder to get that set point until it's oscillating. Yes, you can do it with SysID. You can just calculate with recalc, but if you really want to waste a couple hours of your life, you can manually tune it. And also most people won't probably start at 0. They probably use recalc or SysID, something like that. But when you're trying to adjust from those values, you shouldn't of course take SysID values like from like a silver platter or whatever, take them at face value. You should also be adjusting these, and this is kind of telling you how to adjust them in a way so it is more accurate to your mechanism. Okay, SysID. SysID is a very fancy thing called system identification. And glossary control, system identifier, introduction. And what it does is it allows you to, it basically spits out your values for KP, KV for you. So you input all your like stuff in here, and then what does, it spits out the KV and the KA that you need, or whatever values that you got from it. Let's see here. So, SysID, you can check this out probably on your own later. But in general, you put in your values of your arm, like your SysID, kind of your data that you collected. So what your SysID, you collect a bunch of data points and then you put it into a graph and it does math for you. So it gives you your KA, KS, KV, as well as your PID. Makes tuning a lot faster than manual tuning, but of course, you shouldn't just take these values and then run with it. So that's something you should look at. And then if you don't know what Recalc is an amazing website. Let's see, YAMGen actually provides a link to it, right? Oh, there you go. Recalc. It is a bunch of FRC like calculators and stuff, like your gear ratio. And what you can do is put your motors in here, and then it's going to tell you all this fancy graph and math and stuff. So this is what I was kind of talking about when you're talking about like lining your velocity and your position kind of together. You want to make sure they're following the same slope by adjusting these values. I'm pretty sure. I don't know. It does stuff here though. Ooh, okay. Is this slideshow being available to outside of partner teams soon? Because I can send that in. Yeah, awesome. Oh, I only got 10 minutes later. I'm only on 0.4. 0.5. Okay. Tips. For the gains that are other than kg, you want the mechanism to start moving from wherever its reference set point is to compare the graphs more easily. To do this, set the starting position and let the mechanism get close to it. Then set the kp to do something high to get it to move from the rest of the way, and then set kb back to where it was. 0 until you're at the KP tuning step. KP setting to something high. This is going to be reasonable high, not 1000 high. Unless your gearbox is severely not capable of lifting your mechanism, then you can probably with confidence say it would work with PID 1000. But if your mechanism is only running when it has PID or it has a P of 1000, there's something wrong with your mechanism. So this is going to be reasonable high, kind of, just get it to move. That was what I was doing with YAMGen earlier. I was just like increasing my P till it got to somewhere close I wanted, and then that way I can tune my KG and whatnot later, right? Oh, this is YAMGen, by the way. It's web-based sim that you can input all your motor configurations and your arm specs, and you're able to live simulate it, and also gives you code for those who like copy and pasting. I'm a big fan of copy and pasting. You don't need to KS in sim because there's no such thing as static friction in sim, because why do you have friction in sim when it's everything's ideal? For the most part, you don't need to worry about KS on a well-designed mechanism. Keyword well-designed, meaning that it can lift itself and hold itself fine without much adjustment, especially on elevators. It's more commonly going to be useful for arms and pivots when there is a lot of friction going on, preventing movement. Ki is error accumulator. Make sure to clear the accumulator before setting the value from 0. Once again, restating, be very careful when tuning Ki. Ideally, just set it to 0. But if you do tune it, just be careful. And then live tuning. Let's see. Ooh, okay. There is live tuning built into YAMS. If you're using YAMS this year, this is a big bonus for you. So let's hop onto the YAMS doc. I'm gonna try to keep this within an hour. Of course, that CRT workshop took way longer than that. I don't even remember if I finished it. Okay. Let's see, live tuning. So live tuning, very simple. Make sure you have your telemetry data existing somewhere in your code. That way you're outputting values like your position and whatnot. And then what you're going to do is you're going to open up Elastic, which if you downloaded FRC tools this year, or you have WPIlib, I'm pretty sure this just comes with it. So you can just open up Elastic. If I have Elastic, that would answer a lot of my questions. I do have Elastic. Yeah, it just comes with WPIlib, basically. And what you're gonna do is you're gonna drag and drop the live tuning button. So it's gonna go from smart dashboard to your whatever mechanism you have, arm elevator, whatnot, commands, your subsystem name, and then live tuning. And you're gonna press that big glorious button. Don't press any other command buttons that would trigger a command afterwards, though, after you click on this, because if you think of a command scheduler, think of it as a queue, a line of commands waiting to run, a line of people waiting for ice cream. If you press another button, that is effectively having someone cut right in front of you when you're already in the front of the line, and will cancel your live tuning. And so now you can tune with your robot enabled. So your robot can be enabled and on. You can do this in sim even. And you're able to, when you press that button, you can press another button in Advantage Scope. You don't really, it's not shown in here. I don't want to pull it up though. But there's a button up here next to the search bar. I think it's kind of like a filter. You click on that, and that's how you're able to input your PID values, and then you can just live tune it. You can set your set point, you can increase your P, K, I, and D, and this significantly increases how well you tune or how fast you're able to tune your mechanisms. I was able to tune a arm and sim that I was like struggling to get work for a while using live tuning, and that took like 5 minutes during my pre-calc class, which is pretty great. Really fun. Check it out. Don't use live tuning if you haven't tested your mechanism in sim, because once again, you have no idea what you're getting yourself into. And then once it works in sim, try it on the robot. And yeah, once again, keep your this is important. Keep your PID values that you have in sim separate from the ones that you're using on your actual robot. You can do this with pretty easily right here with your closed loop controller. Oh, I don't have sim on here. Man, I should do that. I'll get internet to do that later. Okay. Load. Noticing flaws in my own programming. This one doesn't have it either. Okay, fine. I'll get it from the climber. Should really check on what my interns program from now on. I have no idea what they're doing. Okay, here, look. With YAMS, you can separate your PIDs to sim, with a sim closed loop and a regular closed loop, and these would basically operate differently, based on sim and real life, because in sim it is different from actual real life. Imagine having interns. I know, right? Last year I was a programming team of 2. Basically started out as 1 though. But honestly, I kind of like the smaller team better. You kind of feel like you're in more control. You spend a lot of time just managing interns rather than actual programming, I feel like, when you have such a big team that are also highly inexperienced. So that's an interesting challenge I have this year. But yep, okay. So that's that, live tuning. Tuning in Advantage Scope, open the line graph, drag them. Okay, yeah, so drag basically your set points and your actual mechanism position to your graph, and then you're gonna click on this 3 lines that was what I was talking about earlier to be able to do your live tuning. And then tuning a Phoenix, that slide's there for you to check out later. And yeah, now you can tune your velocity and whatnot. Make sure you set all your gains to 0 before deploying your tuning. Make them 0 in your code. Once you open the menu in Vantage Scope and expand the drop downs for your mechanisms you want to tune. So yeah, set them all to 0 first before you do live tuning. Unless you use SysID. If you use SysID, you can put your values in there. This is more of a safety measure in case something goes wrong. Right? And then you want to tune the mechanism so going slow and setting soft limits as possible. Okay. Let's see. It's 7 o'clock. I kind of talked a lot about this already. SysID, CRT. Okay, looks like this sounds like a different workshop to do. Maybe another week. Any questions for today? Any questions? Anything you guys want me to go over a little bit more before we call it a night? Will the slides be shared? I mean, I plan on sharing them like right now, unless Strike tells me otherwise. Is he in here? No, he's not. Someone ping him and partner teams and be like, yo, can I share the slides? I mean, I don't see a reason why not right now. I think maybe the slides are these slides are complete. They might have been mildly incomplete. There's so much stuff in here. And it might take a while. So maybe like every other workshop when I have no idea what to do, probably could pull up the slides. Okay. For YAGSL tuning, would elastic thing okay, so YAGSL live tuning. It does have SysID though, so that will speed up tuning. Memes, okay, didn't have to tune Swerve that much, honestly. Usually you don't, but if you do, just you can manually tune it really easily using kind of the same principles. Do it with SysID. There is a SysID to YAGSL. So let me see if I have that in here. Control F. SysID. Ooh. Okay, so that's one of the commands I did not import. Guess I'm going to do that later. Just see some. See the flywheel SysID. That's for YAMS though. So YAMS has, it's very easy to tune or to make your SysID. It's honestly really easy as well. Of course, you're just gonna have to do a little more work than one line of code, because this feels stupidly too easily sometimes. Oh, yay, slides! Are you unable to put that in announcements? I'll put that in announcements another day. But yeah, any other questions? Alright. In that case, I shall end it off here for next week. No, do we do a special for Valentine's Day or nah? Do programmers feel love? I mean, I obviously feel loved. But like, do programmers have Valentine's dates? Do we? Anyways, I'll think about if we're gonna have another one next week or not because of Valentine's Day. But we're gonna end it off today. Thank you all for showing up today. For showing up, learning about PID values and YAMS and YAMGen and all the other tools we have within YASS. And yeah, thanks for all coming. I hope you have a great day. You can end the video now, Jaden.